So in the last video, we are trying to find the response of the system, right? Now, if we move to higher order systems, then we need to know how to divide them into partial fractions, right? So for that, for simple cases, for example, when the roots of the denominator, the poles are real and distinct, it is quite simple, right? For example, if gs is given as simply, let's say some numerator, let's say some constant 5 by s plus a, let me take some variable s plus b, right? And for such cases where a and b are real and distinct, not equal, it is quite easy, right? For such cases, it is quite simple to find the response. I can even just find it through inspection. Like, for example, if I am looking for unit step response, right, then by this time you know that the output s will be equal to this s times s plus a s plus b. So it will be multiplied by 1 by s. The gs will be multiplied by input, which in case of unit step response is 1 by s, right? So if you want to find the time response, I can simply find it out by just by inspecting this, right? How can I do that? I know that if I make partial fraction of this, then it will be some constant by s, it will be some constant by this, and it will be some constant by s plus b. Finding these constants is straightforward, as we have done in the last class, and I know that my output will look something like this. So a by s inverse Laplace transform will be a constant. This will be b e to the power at plus capital C e to the power minus small b. This is how the response will look like, right? So this is pretty straightforward, right? And in fact, you can even do a numerical based on this, that if you have a differential equation, like if you have an ODE which is given as y double dot plus 12y dot plus 32y, and this is equal to 32 times ut. What is ut? Ut is my unit step function, right? Right. So using the Laplace domain method of solving it would be much simpler rather than solving this ODE using any other technique, right? And Laplace domain, what we do is we take the Laplace transform on both the sides, and then we take the inverse Laplace on both the sides, right? So when we take the Laplace transform of this equation, what will this come out to be? Ys times s square plus 12s plus 32 is equal to 32 upon s, because this is ut and its Laplace transform we know is equal to 1 by s, right? So my ys will be equal to 32 by s times s square plus 12s plus 32, right? And this will be equal to, very simply, 32, sorry, this I can make partial fraction, so it will be sum a upon s plus b upon what? So let me first factorize it, right, before making the partial fractions. And I know for this case that this has real roots, real and distinct roots. That is why I have taken this example. So this is s. So this is 12s. 12s I can write s plus 8s plus 4s plus 32, right? So this is actually if I take 4 common, so s plus 8 will be common, so s plus 8 plus s plus 4, right? So this is equal to 32 upon s into s plus 8 s plus 4, right? So this will be a by s, b upon s plus 8 plus c upon s plus 4. These are the partial fractions on which you can do it, and simply my yt, and you can find ABC, right? Yes, in the last video we saw how to find ABC. You multiply this on both the sides and then choose different values of s and find ABC, right? So yt will simply be a plus b e to the power minus 8t plus c e to the power minus 4t. And by this time you know that this is the forced response, isn't it? Because this is from the pole due to the input function, and this is the natural response which will die out with time, right? The next case I will be doing in the next video.